Welcome back. We are now going to start a new section in physiology, which includes the renal system and the nephron, which is a big deal. So let's go ahead and get started. So we're going to go ahead and start talking about the kidney and the urinary system. So the kidney is responsible for quite a few things, like eliminating wastes and regulating medications, regulating blood pressure. Also, it helps promote red blood cells with erythropoietin. So all of those things are in there, and you can go through that, including things like the kidney anatomy. But what I really want to talk about in length is actually the nephron. Now, the nephron is the working unit of the kidney, and there's like a million of them, all right? So when we're talking about the nephron, we're going to draw a picture about it in a minute, but I just want to go ahead and talk a little bit about the different types of nephrons. There's something called a cortical nephron, and then the juxtamedullary nephron. Now, the difference I know between the two is that the cortical nephrons are on the outer side of the renal cortex, and there's more of them. 80% are in the cortical category. The juxtamedullary nephrons are in the inner 1/3, and also they have long loops, and you're like, who cares? Well, the thing about the long loops is then it can make more urine, so I would know that about them. So those are the two types of nephrons. But when we're talking about a nephron, basically what the nephron is, there is a little blood vessel called the efferent arteriole that comes in, makes something called a glomerulus, and then leaves, all right? We're going to talk about that in a minute. But what this is so important for is that this little capillary system then provides the nephron with blood to filter, okay? And we call that glomerular filtration. And remember when we talked about GFR in pathology, glomerular filtration rate, and how we want that high so we can have nice filtered blood? Well, we need to know some things that promote it and stop it as well. So a couple things that favor it is high hydrostatic pressure. We just talked about hydrostatic pressure, but basically how much blood pressure is flowing through. More pressure, more filtration, okay? The other thing is that if you have an efferent arterial constriction, that's going to actually make more blood being filtered because there's sort of a stop there, so it keeps getting filtered out because of high pressure, as well as increased renal blood flow. So those are a couple things that increase our GFR. But what we're going to do now is I want everybody just to take out a sheet of paper, and we are going to draw out a nephron, including some of the things that go on in it. And so what we can do is we're going to take this up to the whiteboard, draw out a nephron, talk about what comes and goes from there, and then after that, go back through your notes and just kind of highlight the different things that we talked about. All right, so let's go ahead and draw this out. All right, so here we are going to start talking about the nephron, and this is also in the book if you don't have a piece of paper. But when we take a look at the nephron, we've talked before about the afferent and efferent arteriole. Notice how the afferent arteriole comes down and makes a capillary network called the glomerulus. Now, then it leaves the glomerulus and comes out as the efferent arteriole. Is this oxygenated or deoxygenated blood? Right, it's oxygenated blood. It is just a filter system so that the blood can become cleaner. Now, we talked about GFR in the past when we talked about pathology. So this is where glomerular filtration rate comes into play. So everything that goes into the nephron is being filtered. The more you can filter, the higher the glomerular filtration rate, and basically the cleaner the blood can be, getting rid of wastes, making more urine. So let's talk about the different parts of the nephron. So the first thing you have is the glomerulus, which goes into Bowman's capsule. And basically that takes all of the fluid, all of the amino acids, everything, and starts to act as a huge filter, all right? The first thing that everything goes through is the proximal convoluted tubule. Now, the proximal convoluted tubule is really where all the action happens. This is where almost all of the sodium and almost all of the potassium is absorbed here, all right? It is seriously the workhorse of the nephron. Also, the things that leave here are glucose and amino acids, bicarbonate, and water. So a ton of stuff. So let's go ahead and write that all out there. Now, look at bicarbonate. Can you think of something else that works here that we talked about within the respiratory system that was a big deal? Right, carbonic anhydrase also is here. Carbonic anhydrase works to also help either eliminate or absorb bicarbonate back into the system, all right? How about glucose? Should glucose continue in through the rest of the nephron? No, right? It is done. We should be spilling no glucose into our urine. So anything that escapes here should be taken from the PCT back into the bloodstream. All right? So let's keep on going. The next thing we have is the descending loop of Henle. Okay? The descending loop of Henle. There's not a lot of things that happen here except for water can leave. And one thing that's kind of crazy is that once water leaves here, it can no longer leave on its own. The only way it can leave on its own from here is if a medication or a hormone is acting upon it. Now we've reached the ascending loop of Henle. The ascending loop of Henle is highly permeable to salts. So it actively pumps salt and chloride from the loop into the interstitium, all right? And that's where it gets, again, picked up by the bloodstream to get circulated back around, all right? Remember, water does not leave here. The other thing, though, that can happen here is that there is a sodium chloride potassium co-transport that can move salts in and out with potassium. This is also where furosemide works. Furosemide is also called Lasix, and it's a great diuretic. And basically, it works here in the thick ascending loop of Henle, and it inhibits sodium chloride potassium from being co-transported. When this happens, you get salts in the ascending loop of Henle, which then water follows it. And we know that water can't escape after that, so then it gets peed out, which is why it's a great diuretic. The other thing, though, that can happen is you get a state of hypokalemia because potassium also stays in the nephron and follows the water and gets urinated out of our system. All right? Okay, so continuing on. Next is our distal convoluted tubule. This part of the nephron is actually located in the cortex. So if you have any questions more about anatomy, I would be aware that it's in the cortex. So again, the DCT is impermeable to water unless it's acted on by a hormone. And in this case, this is where aldosterone works. So what happens is that aldosterone's main job is to take sodium and water and put it back into the bloodstream. So it takes salts and water and puts it back into the bloodstream at the expense of potassium. So if you have a medication that works here, which we do, it's called spironolactone, it actually makes this stop working. So one of the side effects then of spironolactone is also a diuretic. You get salts that remain in the nephron, which then water follows it and gets peed out, but potassium then stays in the bloodstream. And so a side effect of this is hyperkalemia, or too much potassium in the bloodstream. The last thing here that we're going to talk about is our collecting duct. Now, 8 to 10 distal convoluted tubules empty into each collecting duct. We're not going to draw that here, but I just wanted you to know that. So, as previously mentioned, water cannot leave here unless acted on by another hormone. And in this case, it's ADH. And we've already talked about ADH, but no, this is also a place where water can leave the nephron to go back into the body, as well as any sodium or chloride that is left in the system will also leave here. So we've talked a lot about things that are leaving this nephron. Well, where does it go? Well, there's this huge peritubular capillary network, which is an extension of the efferent arterioles that allows things to go back into the bloodstream, and that's called the vasa recta, okay? Basically, it's just like a big net surrounding the nephron where all of the sodiums and bicarbs and glucose can be reabsorbed back into the bloodstream. The vasa recta extends back into the cortex, and then it drains back into the venous system. So that is a lot of information, but what I would do is kind of just lay out your drawing, think about it how it relates to pharmacology, go back through the notes and look at all the bullet points to make sure that you understand just those key details of what we drew out, and I think that you will be ready to roll for your exam when it comes to the nephron. So let's go ahead and take a break there, answer a few questions, and when we come back, we're going to start talking about the endocrine system.